One of the biggest questions in modern day is how we can build computers that work like human brains. This has led to the field of cognitive computing, which is the study of how we can reverse engineer the brain. The goal of cognitive computing is to build a network that is modeled after the human brain. In this presentation, I will discuss the neocortex and the features which scientists and engineers are trying to replicate. I will also cover convolutional network functions and briefly the limitations of ConvNet models. First, I will discuss the neocortex. There are three important features of the neocortex. The first is the surface area, the second is mini columns, and the third are LIF model neurons. The surface area of the neocortex is what determines the cognitive capability of a brain. The greater the surface area is, the greater the cognitive function of the brain. For instance, a mouse has a cortical surface area of around 1 square centimeter, while a human has roughly 2,600 square centimeters of cortical surface area. Surface area makes a difference because of a structure called a mini-column. Mini-columns are cortical building blocks. Many analogies describe them as Lego bricks. However, a more accurate analogy is that they're like tiles, and mini-columns tile the neocortical surface. So the greater the surface area of the neocortex, the more mini-columns in the brain. These mini-columns perform specialized functions. Mini-columns operate in groups in the neocortex. They form cortical areas that specialize in functions, such as visual or auditory processing. An experiment was performed on baby ferrets that proved a hypothesis that mini-columns can adapt. This experiment rewired the brains of newborn ferrets to receive visual inputs in an auditory neocortical area. This area adapted to process visual information. The mini-columns changed the way they functioned so that they could take visual inputs and process them as visual inputs instead of auditory ones. This supported a hypothesis that mini-columns carry a quasi-universal algorithm that they use for adaptive learning. Leaky, integrate, and fire neurons, called LIF neurons, are specific neurons in mini-columns. These neurons are the simplest neurons to model because they communicate in binary, either spiking as a 1 or not as a 0. These neurons have an electric potential within them, and when that threshold of potential is breached, they fire. But if it's not breached, they don't fire. So these neurons are easy to model, and most spiking and non-spiking convnets are modeled after LIF neurons. Convolutional networks, which I will call ConvNets, are artificial intelligence networks used to process and classify images. ConvNets work in three stages, which are often referred to as modules. The first is the edge extraction module. The second is feature discovery module, and the third is the C2 unit production module. The edge extraction module receives direct visual input. It processes grayscale images. This module uses Gabor filters with 4 orientations to produce orientation-specific edge maps. It's like a sketch before painting. This module outlines where the edges of an image are. The feature discovery module finds relevant classification features. The inputs for this module are the edge maps from the edge extraction module. After identifying intermediate features, this module creates a separate map for each one. This step is like the painting over the sketch. If the ConvNet was processing a photo of a dog, the edge extraction module would create a lined image, effectively, of the dog. It would pass that on to the feature discovery module. The feature discovery module would process the image and determine this is a dog's tail. It would then take the dog's tail and create a separate map, like a focus painting, for just the tail of the dog. The final module is the C2 unit creation module. The C2 unit module recognizes the features identified by the feature discovery module. After receiving the many input maps from the previous module, this module produces C2 units, which communicate what a feature actually is. The produced C2 units are sent to the classifier network to be sorted. and these units are both shift and scale invariant. After the feature discovery module produces the painting of a dog's tail, it would be sent to the C2 unit module. This module would process the image and determine that it is truly a dog's tail. This would then teach the network what a dog tail looks like. This creates the shift and scale invariant part of this module. This means that any dog tail image that this network receives could be identified as a dog tail, no matter the size or orientation of it compared to the original image. The ConvNet has a few problems, but the largest limitation with the ConvNet in this study and most other ConvNets is that it only learns in one layer. The neocortex performs learning functions on all of its layers, but the ConvNet has not been taught to extend its learning. For instance, all of the modules I talked about exist only on one level of this artificial intelligence network. But this is not a limit that's on the human brain. One of the biggest struggles of scientists and engineers today is to determine how to create layered learning in AI. But despite these limitations, the ConvNet is useful in training spiking or multi-layered networks. In conclusion, the human brain is an adept processor. The neocortex and its structures are all amazing computing organisms. Despite setbacks in perfect replication of the brain, this study on a ConvNet has shown that replicating the human brain is possible. The day that scientists and engineers are able to fully replicate human cognitive function is not too far in the future. Thank you.